Hello. The video that you are watching is about AC circuits. Let's see what happens if we connect a voltage source, an AC voltage source with a sinusoidal wave of input with a resistor, a capacitor, an inductor, a combination of them in series and in a parallel way. Let's get started with a resistor. As we can see here, the waveforms for the current and for the voltage are, as we can see, in a sinusoidal waveform on the right side. We realize that when the voltage gets the maximum value, the current gets the maximum value too. When the voltage gets zero value, the current gets the zero value too. So what happens in the one quantity, the same thing happens to the other quantity too. So we say that the two quantities, the voltage and the current, are in phase. And we can represent this statement with this phasor diagram. We use these two arrows, vectors, in order to represent the fact that the voltage and the current are in phase. They have zero angle. These two vectors between them have an angle to be zero, are in the same direction, on the same axis. So the phase is zero. As you see here, the voltage is equal to the R to R times I maximum sinus omega t, and the I is equal to I maximum sinus omega t. Let's continue now with an inductive circuit. We connect an inductor with a voltage source of a sinusoidal waveform. The opposition to current flow through an AC inductor is called inductive reactance. You see that the inductor is a component that reacts. What does this mean? When we have here, permit me to explain you a little bit. When we have here a positive and negative polarity in this way for the voltage source, and we have the current from the source to be in this direction, the inductor induces a voltage which we call V induced, which opposites to the increase of the current. So we have an I induced. In the same way that this is created for the reaction. These two. Okay. The I induced opposites to the I and follows the same waveform, but in the opposite direction. So when we change now the polarity of the voltage source, when the voltage source changes its polarity and gives here a current I, according to the Lenz's law, the inductor creates in the opposite direction an I, an induced current, and a voltage induced in this way, in this direction, okay, with this polarity. So the inductor reacts. That's why we say that we have an inductive reactance. We do not have a resistance as in the resistors. We have a reactance. Okay, and it depends on the frequency. We are going to see what does this mean. Here we have the waveforms for the voltage and for the current. Because we have this behavior of the inductor, we have the voltage to lead the current by 90 degrees. This is the expression we use in order to represent the whole phenomenon that takes place during the operation of this circuit. You see here when I have the voltage to the inductor to be maximum, I have the current to be 0, and so on. So this can be represented by this phasor diagram, and the IL is on the horizontal axis, and in the vertical direction is the VL. So we say that we used to say that the VL leads the leads the current, or the current lags the voltage. As we can see here now, the inductive reactance is equal to L omega. The L is the inductance of the inductor. The omega is the angular frequency, and the omega, as we know, is given by the formula omega equals to 2 pi f. So when f is increased, omega is increased, and XL is increased, and vice versa. The XL is the opposition to sinusoidal current in an inductor. When we have a frequency to be very small, we have XL to be very small, so the I becomes maximum. When I have a very high frequency, the XL is very high, and I have almost a current to be close to 0. This reaction, let's say, this behavior of the inductor is used in filters. We are going to see this in another video. Let's continue now. Let's clean our board, clean our drawings. Here we have an RL circuit. We have a series RL circuit in series. As we can see here, it is connected with a AC voltage source with a sinusoidal waveform input. We have here the phasor diagrams, the two phasor diagrams, one for the resistor. You see the I and the VR are in the same direction, in the same horizontal axis, and they have no difference. They are in phase, no phase difference. They are in phase, and the VL to lead the I here. So if we continue in this slide, we can see that if we want to get the total voltage of this circuit, we use vectors. We use the phasor diagrams, as we say. We have the VR in the horizontal axis, the VL in the vertical axis in a perpendicular way, and we have the resultant to be the V total. As you can realize here, this rectangle here can be represented with this voltage triangle. And how we calculate the voltage? We calculate it with the use of the Pythagoras theorem. So the V squared, the V total, let's say, from the source is equal to VR squared plus VL squared. As a result, we get that the V equals square root of VR squared plus VL squared. Okay, this is the way that we calculate the voltage. I need to make a reference here to the DC current when we had R1 and R2 in series connection with a DC voltage source here. We used to calculate, we calculate the total voltage by this sum, V1 plus V2. But now, when I want to calculate the total voltage of all the components of the circuit, and in this occasion we have the RL circuit, we do not go straight to add these two values, the VR and the VL, but we use the squares. You see, here I have the V squared to be equal to VR squared plus VL squared. You see, if we compare these two circuits, we can see that we use these squares here because we approach this with this rectangle, with the phasor diagram. Okay. Now, when we have to find the impedance of the circuit, we have this triangle now. This is the Z, this is the R, and here we have XL. So as you can realize, when I have the triangles, in the horizontal axis refers to the resistor here and here. Here was the resistor, the resistance of the resistor. Here was the voltage of the resistor. The vertical axis now refers to the reactive components. This is the VL, and here is XL. Okay, and the total values are given by this resultant. Okay. Let's have an example now and explain a few quantities such as power factor, dissipated power, reactive power, apparent power through this example. Okay, I will present you these quantities: the reactive power, the apparent, the dissipated power, the power factor, the RMS. Okay, with the use of this example. So we have an RL series circuit with the R to be 5 ohms, the L to be 60 millihenry, and it's applied by alternate active voltage, or RMS, as we used to say, to be 10 volts and 50 hertz. We need to calculate the impedance, the RMS value of the current, the RMS values of the VR and the VL, the power factor, the dissipated power, the reactive power, and the apparent power. So let's start step by step. The impedance of the circuit. The impedance of the circuit equals to Z square root of R squared plus XL squared. Now XL squared, XL equals to L times omega. L times omega equals to L times 2 pi F. So if I substitute, the L is 60 millihenry So I write it in this way, 6 times 10, this is 60, and the milli are 10 to the power of minus 3, times 2, times 3.15, times 50. So here we have 2 times 6, 2 times, let's say 2 times 50 is 100. Okay. So this packet here gives me 314. And here I have times 6 times 10 to the power of minus 2. Now we have as a result we get 0.8 ohms. Okay, we substitute this value to Z and we have 5 squared plus, or we can use 19 here. Okay, we are going to make a rounding of this number, 19, almost 19 ohms. 19 squared, which is equal to 25 plus we get here 361, which is equal to square root of 386, which gives me 19.6 ohms. And this is the impedance of the circuit. Okay. Let's continue with the other question. The RMS value of the current. Now, what is the RMS value of the voltage and the current? The RMS values are used in order to represent, let's say, the equivalent of the AC current with a DC value. So you see the voltage has this form, generally speaking. Okay. And we can see here that the voltage changes with the change of time. So this value that we get from this equation is an instant value, but we need one value to represent all the phenomenon. This value is the RMS value, and it is a DC value and has the same heat results with the voltage, with the AC voltage. Okay, the RMS is, let's say, the equivalent of the in a DC way of the AC current. Okay, we use the RMS in order to represent, let's say, the AC voltage and AC current with the use of the RMS DC value. Okay, now these values, the VRMS, let's say, generally speaking, it is Vmax above square root of 2. And the IRMS, in the same way, equals to Imax over square root of 2. So this is the way that we calculate these values. Let's find now, let's calculate the IRMS value. the I RMS equals, now we are not going to use the expression that I have already shown you. I will use the Ohm's law, where we have the VRMS above Z. We have already calculated the voltage is 10 volts and the Z is 19.6, which is almost 20. So we can see that it is almost, let's put this sign, this symbol, almost 0.5 amperes. Okay, we make some roundings in order to simplify our calculations. So 0.5 is the IRMS. Let's continue with the other question. C. Here we have the RMS values to find for VR and the VL. According to the Ohm's law again, we use I times, which is IRMS also, okay, times R. The IRMS was 0.5, was found, 0.5, and here I have 5. So it is 2.5 volts. The RMS value for the voltage on the resistor dissipating. Now the VL, the RMS value for L equals to I times XL. This is equal to 0.5 times the XL was times 19, which is almost, and I say almost because we have done already some roundings to 0.5 and so on. So this is 9.5 volts. Okay, so the VR equals to 2.5 volts and the VL equals to 9.5 volts. Let's continue. It is simple, that just we need to understand what happens step by step. Now the power factor. The power factor, if we draw here the vectors, here is the vector of the resistor, and here is the vector of the inductive reactance. And here we get the resultant. I will use this color. Okay. As we can see here, here is Z. Here is R. And here is XL. And here is theta. So the power factor is cos theta equals to R above Z. We make the calculation. 5 over 19.6, okay, which gives me, permit me to round it a little bit to make it 20. So almost 5 above 20, which is 0.25. And this is a very bad power factor. Okay, we need the power factor to be over 0.9. Okay. Okay, the power factor, actually, we are going to see the use of power factor when I explain you in the next questions, the powers, the kind of powers we have, the reactive power, the true power, and the apparent power. We are going to see there which is the role of the power factor. Permit me to explain you in a little while. Okay, let's continue now. Clear this board and continue to E, the dissipated power. Okay, the dissipated power is the true power. The dissipated power is the P of R, of the resistor. And we can write it just P, which is equal to V RMS times I RMS times cos theta. Now, if we substitute the values of VRMS and IRMS, we have already found them. We have the VRMS to be 10 times 0.5 times 0.25. So we get 5 above 4 times 25 times 25, 1.25 watts. This is the dissipated power, the P. Okay, that this power we call true power. The dissipated power, the power on the resistor dissipated by the resistor, is called true power. This is the true power. Okay, let's continue with the next one. We have now the reactive power. The reactive power is actually a power that we do not want to have in a circuit because it has no use. Okay, the reactive power equals, it is symbolized by Q, and it is VRMS times IRMS times sinus theta. So we substitute 10 times 0.5 times. So for the sinus theta, as we remember, I will use again the triangle and the resultant. We have here the Z, here the R, and here the XL. The XL is 19, almost 19 ohms. The R is 5. So we get from theta, the sinus of theta equals to XL above R. So it is 19 above 5. We get 19. Now, what is the unit? The unit for the reactive power is VAR. Okay. And it's a power that we do not want to have because it has no use. It's like having a glass of beer and you have the foam. You have here a glass. Here's the part of the beer. Here's the beer. And here, over here, we have the foam. All this part is covered by the foam. We pay for this. This represents, the foam represents the reactive power. We do not drink the foam. And this is the true power. This is the power that we need to have. Okay, this is what we pay. We pay for all of this. But our target is to have the less reactive power that we need to have in order to have better performance, let's say. Okay, let's continue now with the apparent power. The apparent power is that total power that I have shown you in the previous slide with a glass of beer. The total power is called apparent power. And if I create the power triangle now, I have here the S, which represents the apparent power, this one. I have the Q, which represents the XL, the reactive power. Here it could be a capacitor also, XL, XC components. This is the side of the triangle that has to do with the inductors, capacitors, and their combination. Reactive power here. And here we have the P, which is the true power. Okay, the true power. So we need to have as less reactive power as we can get. Okay, so we use some techniques in order to decrease this Q, the value of Q, and have more true power. So the apparent power, as we can see here, equals to P squared plus Q squared. Okay, S equals to square root of P squared plus Q squared. As a result, we get the values that we have already found. We substitute. So we have the P to be 1.25 squared plus the Q that we have already found, that it is 19 squared, which gives me finally, this is almost 19, okay? And why this is almost a 19? Because here we have 1.25 squared. So we get a value near to 19 for this square root, which means that we have a very bad, as we have already found, we have found that the power factor was very, very low, was 0.25, the power factor, which is very low. Okay, very bad performance. Okay, the power factor can be found also, but this is just an example, okay? Cos theta equals to P above S. Okay, so the cos theta is P above S or VR above Z, above V total, or R above Z. You see, this triangle could have here either the value of R or the value of VR in this side. Here it could have not the VR, excuse me, excuse me, it could have the value of Z and the value of V total. On this side now, it could have the R, the value of R, and the value of the VR. On that side, we could have the XL or the XC, okay, or their combination XL minus XC. We can have also the VL, the VC, or the VL minus VC. And here the XL minus XC. Anything. Okay. So this was a characteristic example that we can expand it and use it as a path in order to solve similar exercises for RC circuits and RLC combinations. Okay, but these examples we are going to see in next videos. Thank you very much.